racing shell. It's surely one of man's most elegant creations. Its form and function are so beautifully matched, it seems there's no room for improvement. And yet that's not what a group of rowers, engineers, computer programmers, and boat designers think. Their aim simply is to create the fastest racing shell ever built. Mike Vespoli, a former Olympic rower and coach, began his rethinking of the racing shell by going back to basics. The key problem is overcoming the resistance to the boat's movement through the water.
One of the things we try to achieve is, at the end of each stroke, that there'd be no resistance, and that's a lot harder to get between a technique and the boat than you'd think.
The big reason it's so hard is that there are two different sources of resistance. The first is simply friction between the part of the hull under the water, called the wetted surface, and the water itself. The second source of drag is the turbulence created by the bow and stern as the shell cuts through the water. The trick for the boat builder is to create a hull shape that cuts down both sources of resistance at the same time. Historically, that's proved very difficult. But Mike saw that it was time for science to lend a hand.
Hulls have evolved eclectically for 100 years, and it's only through modern research now that have we been able to test things to determine what the limits are, both in terms of hull shape and in terms of minimum resistance.
The value of the scientific approach was spectacularly demonstrated by the design of the America's Cup-winning sailboat, Stars and Stripes. So, Stars and Stripes designer Bruce Nelson was called in to find out what it's like to row in an 8-man shell. As Bruce quickly found out, a racing shell poses very different challenges from a sailboat.
What was that, Bruce?
Yeah, we're rocking a little now. Crossed a few wakes there. These things like to roll.
What are critical in a shell are rhythm and balance.
You can really sense how the balance and the timing of the oarsman controls the performance of the boat, and getting the boat balanced out, you're going to be able to put a lot more energy into pushing the boat forward than when the boat's out of balance and rolling around. You're struggling just to keep the boat upright.
If there's one basic requirement of a shell, it's that it should not sink. And that means the hull volume must be big enough to float a 2,000-pound crew. But if hull volume can't change, its shape can. Using a sophisticated computer program, the design team explored the consequences of stretching out a standard racing shell by a full 2 feet.
We were able to make the hull shallower in the ends, in particular the bow sections, which enable us to make the sections rounder and reduce the wetted surface.
By floating higher in the water, frictional drag is reduced. Then Bruce sharpened the bow and stern to make the shell cut the water more cleanly, reducing wave drag. The result is a longer, sleeker boat than any in existence. And according to the computer, it should also be faster.
The oarsmen certainly like to have any slight advantage they can in equipment, and we calculate that our shell design produces an advantage of approximately 3 seconds over this 2,000-meter course, which translates to slightly less than 1 boat length.
But are the computer calculations correct? To find out, a 1/3 scale model of the new design is being tested in a football field-sized tank, usually reserved for testing models of Navy ships and oil drilling rigs. A motorized carriage tows the model as sensors measure how much force is needed to drag the hull through the water. But the existing rig is designed to tow models at a constant speed, while racing shells move in spurts, surging forward with each stroke of the oars. So the tank engineers designed a carriage that would precisely mimic the real motion of a racing shell.
We've tested over a speed range from about 5 knots up to 12 knots, which is an typical Olympic rowing speed, and with rowing rates of 35, 38, and 42 strokes per minute.
Then the key test, comparing the new hull shape called the D shell with an existing Mike Vespoli boat, the B shell. Being able to test the hulls in the surging mode proved crucial.
When the boats were towed at a constant speed, the B and the D were very close to each other, almost within the experimental accuracy, with the D only slightly better. When the boats were tested with surge oscillations like they would be under real rowing conditions, there was a clear advantage to the D.
So far, so good. The computer predictions stood up under the conditions of the tank test. But now, as Bruce ships the blueprints for the D shell to Mike Vespoli's Connecticut shop, comes the most important question of all. Can the new design be built? Remember, the D shell is longer and sleeker than any boat built before, but a successful shell must also be light and stiff. So Mike turned to materials usually reserved for building high-performance aircraft, like carbon fiber and nylon honeycomb.
We use a honeycomb core, which, by thickening the hull, increases the stiffness of the hull. It's much like taking 3 pieces of paper. Independently, each one of them is flexible, but when put together, you can have something like a sheet of corrugated cardboard. It's a similar principle.
The honeycomb core is fitted to the fiberglass, carbon fiber, and epoxy shell to create a 205-pound boat that's baked to completion overnight in a giant oven. Of course, the real question is whether the new boat is faster.
50 to go. Keep pushing it. Keep pushing it.
Coach Curtis Jordan puts the crew through its paces on each boat in turn. And the second run in the D shell was faster despite worsening weather conditions.
And they were still able to improve the speed of their second 500.
Their stroke race in the second 500.
Mike Vespoli's job is done. Now it's up to Coach Jordan and his young team to make the best of the new shell.
I like the way it looks in the water. A lot of the rowers like the way it feels. And in theory, it should be a faster boat. We lost a silver medal by 0.3 of a second to the Russians in Korea. If we were 0.3 of a second faster, if we were half an inch per stroke better, we'd have beat them. So it makes a big difference.